Hello, calculus students. This is Mrs. D here to talk to you about separation of variables. This is an important process that you will need from time to time, but do not overuse it. You do not always use it. And this is our first goal, knowing when to separate and when not to. There are lots of things in life that are separated. For example, your laundry. You probably want to separate your clothes that are white from your clothes that are not white so that they don't intermingle in the drying process and have colors come out pink instead of white. I did that once. Other things that are separated, we separate at assemblies. Freshmen in one section, sophomores in another section, you get my point. So, when do we need to separate? Anytime you have more than one variable, and in this case, my variables are x and y. So this is a great problem to start with. We're going to separate the variables, and then that will help us in our solving process. That will be the next goal, is solving. So I have y on one side of the equation and x and y on the other side. So the goal would be to get all the x's on one side, all the y's on the other. So I'm doing just like I can with any equation, the same thing to both sides to maintain balance. Here I've isolated dy, but notice there's still y on both sides of the equation until I divide. So we have dy over y equals dx. Now it's a little bit of a jingle. I haven't gotten a copyright on it yet, but we are separating, and then we will integrate. Integrate is a verb. It's the act of finding antiderivatives. The action word for finding derivatives is differentiate. This word is integrate. We will be finding our antiderivative. Very simple two-step process. Integrating both sides, we end up with the natural log of the absolute value of y equal to x. This is like a 1, right? Antiderivative of 1, constant rate of change 1, that would be the function x. Of course, there could be a constant added. That constant, I would recommend that you only put the constant on one side of the equation. Now, nonetheless, we have done the separating, the integrating. We do not have a solution yet. Normally, the solution is the function y equals something. I'm going to move all my work up. Let's see how that works. Ooh, slick. It almost all moved. It still is almost all moving. Okay. Solving. To get y by itself, I'm going to use the exponential function, which is the inverse function to the logarithm. And now I have y equals e to the x plus c. Notice that c is in the exponent now. And I'm going to rewrite. This will be commonplace for this type of problem, which you're going to see a lot of in this section. I'm rewriting it with the property of exponents. Oftentimes we go this direction, where we see the two exponents and we add them. This time, I'm kind of breaking it apart. And that tells me that here, e to the c, it's just another number, right? It's just another constant. So my answer will be c e to the x. Y equals c e to the x. And this is just a general solution. We would need more information to find a particular solution. Here's another problem. Now I'm going to make this a situation where we can find a particular solution. So we're going to be given the point 1, 7. Let's see how that works out here. So this differential equation, we're going to solve it. Those will be your directions. Solve the differential equation with the initial condition, 1, 7. So I'm just picturing like a slope field, and this one little point is going to help me to realize, oh, that's what the curve looks like, or that's what the curve looks like. All right, let me get that out of the way so I have some space to write. Let me try to erase it and have it not erase. Okay. So let's separate the variables first. dy, I'm going to divide by y squared. I would not recommend that you ever divide by the dx or the dy. It's going to be really awkward when you try to find the antiderivative. And then we have x dx. Now that we've separated the variables, we will be ready to integrate. And then the last part of our solving will involve these two numbers here. We'll get a very nice solution this time. So integrate, antiderivative of x is 1/2 x squared plus a constant. My favorite place to put the constant is on the right-hand side, or wherever x is in this case. The antiderivative of 1 over y squared. Do not be fooled into thinking this is a logarithm. It is not. That is just a negative power of y. Maybe picture it like that in your mind. So we would have y to the negative 1 with a negative multiplier. This will be a little bit strange at first to solve for y. I'm just going to write y to the negative 1. I'm going to divide both sides by a negative. And the constant says plus c, but for all we know it's a negative number. So if you divide by a negative, it's still some number or some constant. This basically says the reciprocal of y is this quantity. So if we'd like to find y, just y, the reciprocal of a number is the reciprocal of another number, and then it's its own reciprocal. We could just multiply both sides by y. Let's do that instead of all that jargon. Now I don't have y by itself, but I will notice that I need to do some dividing now to get y by itself. And it's just another reciprocal type expression. This 1 is going to be divided by that quantity, negative 1/2 x squared plus c. Looks like a solution, but we still need to use this coordinate. This input is paired with this output, and that gives us a particular value for c. What is that particular value? Let's SEE. So we have 1 over negative 1/2 times 1 squared is 1. Seems to me we're probably going to have to be subtracting a number here to make this work out. Let's see, if I multiply both sides, I would have 7 times a negative half plus this unknown number would have to equal 1. Maybe 1/7 if I divide by 7. And lastly, I will have to do some adding, add 1/2. So looky there, it's not negative at all. But it is smaller than a half. No, it's smaller than 1. Let's get 14ths here. So times 2 times 7, I will have 9/14 for my constant. So to write your final answer, should be an equation set equal to y, and it should be as specific as possible. Having a point here, we're able to also find the constant, so it will be 1 over negative 1/2 x squared plus 9/14. There's your final answer. Using the initial condition, we solve for the constant. On this slide, we are going to explore different ways to separate. Could be a good time to pause the video and try to separate the variables. These two differential equations look very, very, very similar, but they're actually going to be very, very different. So I would pause and try to separate the variables. Waiting for you to pause. Okay, now that you're back, let's see, did you get y dy equals negative x dx for this separation? And do you have dy over negative y equals 1 over x dx for this equation? All we've done is separate the variables. Now let's try that step of integration, or finding the antiderivative. Ooh, this one's going to be fun. On this one over here, we're going to get the natural log of the absolute value of x. Then we're going to have negative natural log of y. That's funky. I'm drawn to this one because it looks interesting. As we try to solve for y, don't get too excited and do things out of order. We will still need to use an exponential function, but not yet. The exponential operation, I can't do that really here to get y by itself until I get rid of that negative. So I'm going to divide by a negative 1. And again, that constant is still just some number. So I have negative natural log of x plus c. And then I'm going to write what we have here is still natural log of y. Now is the time to use that exponential, e to the, that's an arrow that got sad. Now we have y equals e to the negative natural log of x plus c. Notice that constant is in the exponent, A person could also write this, if you break it down, as c e to the negative natural log of x. Or if we use a property of exponents real quick, negative natural log of x, this could be rewritten as a power of x. Natural log of 1 over x, basically. So I like this answer to be written in this form. It would be y equals c e to the 1 over x. No, I don't like that actually. Pausing, making a mistake, learning from it. Why did I just do that? I just did that so that I could see this is e to the natural log of something, and then they would undo. So actually we just have c times 1 over x. Lesson learned. That's a fun one to check. Go ahead and check if you take the derivative, do you get this negative y over x? Solving on this one, after separating the variables, we just have a little power rule, 1/2 y squared, negative 1/2 x squared, don't forget the constant. And then this one's kind of cute. You solve for y by multiplying first by 2, and then you could do one of two things. You could try to take the square root of both sides, keeping in mind that you would get a positive root and a negative root. Or you could just bring these two friends together, add x squared on the other side, and realize this is the equation of a circle. It really isn't a function at all. But, again, this is kind of a general solution. We could also write plus or minus, that includes the top and the bottom half of the circle, c minus x squared. Either one of those would be nice specific solutions if you had constant that you could solve for. Again, you would have to know some condition, x, y, in order to do that. I hope you've learned how to separate variables. You will integrate and solve these differential equations, finding a specific solution or a general solution for y. This is Mrs. D signing out.